Okay, welcome back everyone. So yeah, this is the second part of my tutorial on multivariable data cubes in R. And this time the focus is on how we can combine data from different sources, from different satellite image products, combine them into a single data cube and then make analysis of these combined data cubes much easier and thereby all that kind of stuff. So I prepared two concrete examples for the study case. One is on modeling NDVI values from different satellite measurement missions, and the other example is on well, building a combined data cube from different variables, actually. So on my GitHub page of this tutorial, actually, you see the R Markdown documents and also the rendered HTML output. And this time, compared to the first part of the tutorial, I'm not going to execute everything live here because it just takes, well, a minute more per chunk. So, and I don't want to wait that long. But other than that, we have plenty of time in this part of the tutorial. So I'm going to present these two examples, but then the third part of the tutorial, which we'll also discuss later, has a short summary of what we've learned today. And also, there will be enough time for you to try out things with the example data set. And I even prepared some practical exercises for you. So if you haven't yet downloaded the example data set, probably it's a good idea to do during the part now, so that you can readily start in the second part of this session, actually. Okay, so as I said, this is another Markdown document, actually, which is rendered into HTML. But in this case, I'm not providing the original data used in this R Markdown file because it's actually a mixture of Sentinel, MODIS, Landsat data, global precipitation measurement mission data, and data from ESA on soil moisture. So this is also, well, some data volume, and in this case, I didn't prepare well, data for you to try out easily because it was really time consuming to do. So anyway, all these data are on my actually external disk, and I can show you live later on if you are interested in. So I would say that I'm gonna demonstrate the example on multivariable data cube now. Then we'll have enough time for you to try out things, and then you can work also on your data if you want, and we'll have a really practical session, and I can come to you and we can discuss if something does work or look in depth into some of the functions of the package if you want. Again, if there are any questions or comments, feel free to interrupt me at any point or, well, raise your hand and we can discuss during the session as well. Okay, so the first steps when we want to work with our examples now is, again, that we need to load some R packages. Primarily, it's a gdalcubes package again, which, well, had a comprehensive introduction in the first part today. We again use the gridr package for the pipe operator to make these longer chains of data cube operations easily readable. And then we use a color space package for these nice looking color scales, which have pretty reasonable defaults. And then let's start with the first example. So what we want to do, we want to build a combined data cube from Sentinel 2, Landsat 8, and some MODIS data. So the idea is actually the we use Sentinel 2 level 2A data, so the spatial resolution of the NDVI bands of the red and near infrared bands 10 meters. It has a revisit time of 5 days. So at one location, you get time series of 5 daily time series, essentially, and the file format is JPEG 2000. But actually, I told you in the first part already that we don't really have to care about file formats because we have GDAL, and GDAL does, well, know every format actually, which is relevant out there. So the second data set is Landsat 8 surface reflectance data. It has a spatial resolution of 30 meter in the NDVI bands and a temporal resolution of 16 days. It's about the format of the Landsat data is a bit easier to understand. It's just per image one folder with GeoTIFF files per band and a few additional metadata files, but not as complex as the Sentinel data. And then we're using the MODIS data, in particular the MODIS 09GA product, which has a spatial resolution of 500 meter in the NDVI bands and a temporal resolution of 1 day. So, and the whole idea is to somehow bring together the high spatial resolution of Sentinel data and the high temporal resolution of MODIS data. So that being said, I'm not presenting some very cool analysis here. So the method I will explain to you are very simple and straightforward, but I want to rather show you how this is possible. And then I think for you, it's relatively easy to see what else could be done and how else you could improve the method I'm going to present. So this is really, the method itself is pretty easy and straightforward, but of course, if you don't use the DataCube representation and the gdalcubes package, it's a lot of work which you have to do around the actual method. And I'm showing you how to simplify that. So our study area covers a region around Münster in Germany with mostly agricultural areas and some smaller forests. So at first, let's start with an overview of the available data. So as I said, the data is just on my external drive here. So it's, let's start with the MODIS data. It's HDF files. So I'm going to list all the files available in this subfolder. Again, scan the directories recursively and then look for HDF files and return the full path to the images and then print some of the images. And you see that you have quite a few HDF files. In total, it's 214 images. So it's only one MODIS tile because these MODIS tiles cover a pretty large region. So they're projected in this MODIS sinusoidal projection. And you'll see that the area is actually pretty large that they cover. So then I'm gonna just quickly check how much data this is. So I sum over the file sizes of the MODIS files and convert to gigabytes. And that results in something like 25 gigabytes. So it's not too big, but still it's, well, not something you put easily into your main memory of your laptop. So let's go on with the Landsat files. So we again list all the Landsat 8 files we have. So this is the new Landsat dataset. So it's not the one we used in the first part of the tutorial, which was in the Brazilian Amazon forest. So now we're looking again for GeoTIFF files in this directory on my external drive, and again list all the path to the files, to the GeoTIFF files, and then print it. So that's the path, and in total, these are 270 files, but as you remember from the first part of the session, so one file in MODIS is actually only one band, and it has like 10 different bands, one data set, one image, so that means we have 27 images only. So I again compute the file size of the Landsat data sets, and that sums up to 41 gigabytes, so still not as large as we tried with in the first part of the session, tutorial. And then let's go on with the Sentinel data. So we list these Sentinel files, and yeah, they are also located in a directory on my drive. One thing I have to mention here is that they are downloaded from the Copernicus Open Access Hub, so they are still zip files. So I'm not going to extract it. So I'm working with a zip file directly. And there are actually two reasons for this. The first reason is actually the Sentinel-2 files don't seem to be compressed in the zip file, so it's just as an archive, but no, it doesn't apply compression to the zip algorithm there. So it's not really that you need to extract or uncompress the whole image. It's rather just a container for the subfiles. And the second reason is that GDAL can directly read from zip files and other archive files. So you have in GDAL these virtual file systems, and one is VSI zip. And if you append something like /vsi zip / to the path, it will automatically go into the zip file and is able to get imagery out of the zip file. Okay, so I'm listing the files, or some of the files at least, and see that it's 108 Sentinel-2 images, which then, of course, sums up to a larger amount of space, which is 91 gigabytes. So yeah, if you have a further look at these Sentinel data, we can see that they come from 3 different Sentinel-2 tiles, and they cover already 2 different UTM zones. So although we have a pretty small area of interest, so that was the screenshot I've shown in the plenary. So we have a very small area of interest, but it's still like the tiles can still come from different projections. So, and that's something we need to take care of. And actually we don't want to, so we need to somehow. So to make these data accessible in gdalcubes in the package, what we need to do again is creating image collections first. So again, this just opens all the files once, but not reading any image data. So it just extracts metadata and it knows somehow with these collection formats we have discussed how individual files belong to the collection. So which spectral bands they contain and when they were recorded. So yeah, so this sometimes requires a bit of research because you need to check, is there a collection format available for my data? And probably in most of the cases it is not, but in our case, of course, because I prepared the tutorial, I also created collection formats for these data, so it's already available. So for instance, for these MODIS data, I created an image collection with this line, so modis.collection equals to create image collection. Then I provide the files, and then I specify the collection formats, which is mxdo09ga. So that works actually for Aqua and Terra MODIS products. So they have, and that depends on whether the file name has an O or an Y, I think. So they work actually for both. And then I store the image collection in a file with this name. So and again, this is the image collection file, like the index, which knows which images are actually where and when. And so this is not taking too much memory. Right. So one thing with these MODIS data and the HDF file format in particular is important to note. It's that GDAL exposes the individual bands as so-called sub-data sets. So it's not like you get GDAL understands the different bands as bands, but sub-data sets because they also can have different spatial resolution and so on. Actually in the collection format for these MODIS products, there's the information that use all the sub-data sets from the HDF file. And then it works directly with the sub-data sets, so you don't need to care about this. Okay, once we did that, we get an image collection, we can load it once stored, and you again typically do this only once. And then what you get is a GDAL image collection object, and that in that case references 214 images with 9 bands. And then you get, if you print it, you get some of the images as output and some metadata, so like their spatial extent, their recording date time, their projection, and also the bands. Yeah. No, it's a different data set. So that's the MODIS data set. So you get 2 quality information bands actually. So one at 500 meter resolution, one at 1 kilometer resolution, and then the surface reflectance bands. And the nice thing about these HDF data is you get measurement units automatically in the metadata. So that is cool that GDAL understands that this is reflectance, for instance. Quite similarly, we do things with the Landsat data. So we again compile an image collection from the Landsat data. This is the same format we've just used in the first part of the tutorial. And so we use the same collection format, and afterwards it again shows us the image collection, which contains 27 images with 10 bands. And yeah, that's it. That's 7 spectral bands actually, and then some metadata imagery from atmospheric correction. And then finally, we create the image collection for our Sentinel-2 data. So for that, we use the collection format Sentinel-2 level 2A. And that automatically finds out that, hey, this is a zip compressed imagery. So I'm adding these GDAL virtual file system before the imagery. So that works also automatically. You don't need to specify anything. Right, then this image collection contains 108 images with 15 bands. So yeah, some of them are actual spectral bands, but some of them are only some metadata. So for instance, aerosol, optical thickness, water vapor, and the scene classification layer. For Sentinel data, the scene classification layer contains information on cloud coverage, for instance. So if you look for Sentinel-2 level 2A SCL, then probably you get the information which you will later need to know to define a mask. So to filter out cloudy values. So I think at the end of this page, there's actually a table which tells you which value of the scene classification layer band means, well, what. So in this case, for instance, we try to remove the cloud shadows, cloud medium probability, cloud high probability, and maybe also saturated or defective pixels and so on. So, but that's something, yeah, you often have to look up at the handbooks or manuals from the data providers, actually. So let's go again to the Markdown document. Where is it? Yeah. No. Yeah. So yeah, now it's time to define our cloud masks and quality masks so that we only come up with values from all the senders that are not cloudy and don't have any other values we don't want, actually. So for MODIS data, this is even a bit more complicated. This MODIS data has quality information in so-called bit fields. So they encode a lot of information actually in one band. So they have something like 2 byte values, but you need to extract only the values of certain bits of these values to find out whether the quality is okay or not. So and that's also something which is possible with this image mask function. So what you can do is you say the quality band of our data set is a state 1 kilometer. And then I'm only interested in the least significant 2 bits of this value from this band, which is bits 0 and 1. And then, and that actually applies a logical or bitwise AND operation to the values of these band. And then I'm only accepting values of zeros. So only if the bits 0 and 1 together as a number result in the value 0, we say the values are okay. So that's a bit confusing, but that's how MODIS quality information is actually encoded. So again, you need to carefully read the instructions from the MODIS handbook. So in this case, 0 means just we only use the best observations we have. Right, for Landsat 8, we use the same mask as we have used in the first part of the tutorial. So we use the pixel QA bands and then copied the values from the Landsat 8 handbook, which represent clear conditions. And for the Sentinel-2 data, we apply a mask based on the scene classification layer band, SCL. And we say that values 1, 3, 8, 9, and 10 get actually masked out. So if a pixel has SCL band values that are among these, then the band values of all other bands are actually set to an A. So and these represent, I think, saturated or defective cloud shadows, and yeah, this cloud medium probability and high probability. Okay, so we have image collections and we have masks defined. So let's think about how our target data cube should look like. Or well, maybe before, let's just look at the data and their actual spatial extent, because this varies actually quite a bit. So what we do first to get an initial overview of the data, we create 3 separate data cubes with separate data cube geometries. So we do this first for MODIS. So we create a cube view, which represents our target data cube geometry. Say that we want the spatial temporal extent comes from the full extent of the image collection. We say that we only want to look at the data at 5 kilometer spatial resolution. So for an initial overview, we just use Web Mercator reference system projection, and we look at the data at monthly resolution. So and then we aggregate. We compute the median value per month if we have several non-cloudy pixels per month. Then we computing the median. And the spatial resampling is actually averaging, because originally the resolution is higher, it's 500 meter, and then I'm actually, what we do is creating the average of around 10 by 10 pixels. Okay, then, yeah, I'm just creating an RGB plot first, and therefore you have to find out which bands represent RGB colors. So we create a data cube with data from the MODIS image collection with the data cube view we have just defined, and apply the mask we have just defined. Then we select only bands 1, band 4, and band 3, which are actually red, green, and blue. And then we plot it. And there's another plot parameter I haven't discussed in the morning, which is ncol equals 4. That means that the plot layout gets 4 columns. So usually it tries to derive some good value automatically, but sometimes it may not work, and then you can specify it manually if you want. Good, and this is how it looks like. So this is monthly aggregated MODIS RGB composites data cube from only a single tile of MODIS, so it's actually not really needed to process this with gdalcubes because it's actually already a cube or stacked. But it's anyway nice to have it because it does this temporal aggregation automatically, and also because we want to join it with our Landsat and Sentinel data. Okay, so as you can see, the spatial area is actually quite large, but this is how you get the files. And even if you're interested only in a small area around Münster, you just download these files, and this is the spatial extent of the files. So you can't change something like this. All right, so let's do a similar thing for the Landsat dataset. We define a cube view, a separate cube view now, just to get an initial overview of the data we have. We again compute the spatial temporal extent from our image collection. We say that now we want to work on 500 meter spatial resolution, and again aggregate values monthly. We again do average resampling and median aggregation over 1 month. And then in this case, it spans 2, 3, and 4, representing a blue, green, and red. So we have to reverse the order in the plot function to get actual colors. And then this is how it looks like. So you can actually see that there are very few data available, even if you aggregate monthly, and that there are a lot of clouds actually involved. So yeah, but this is, well, actually that can be expected from Landsat because it's only like revisiting the same location every 16 days. And then if then there's a day with clouds and 16 days afterwards again, then you don't have a value for that month. So that's how the Landsat data look like. And then next, let's look at the Sentinel data. So we create a separate data cube view. Again, use 500 meter spatial resolution, aggregate monthly, do the same resampling and aggregation, but just, well, use the Sentinel-2 mask, so the scene classification layer, the Sentinel-2 image collection, and the separate data cube. And in this case, again, it's also bands 2, 3, and 4, and plot the RGB channels. And well, there we actually see that there are more observations available. So yeah, that's our separate data sets we have now. But now it's actually pretty hard to bring them together because we looked at MODIS at 5 kilometer spatial resolution. We looked at Landsat and Sentinel at 500 meter resolution. And also the spatial extent is pretty much different. So we somehow need to think about our target data cube, how it looks like, and at which resolution and which spatial and temporal area we are actually interested in, and where do we want to analyze our data set. So that's what I do now. So I create one data cube view, which is with a UTM projection, with a UTM zone that is appropriate for that area, decoded as EPSG code. We then specify our area of interest, that is, well, by some left, right, bottom, top coordinates, and also by the starting date and the end date. So we are only interested in the time from April until the end of October. And then we are defining one data cube view, but now the difference is that we reuse it to create the data cubes from the separate image collections.
Maybe this is the missing values.
Yeah. Well, they're just NA, so. Oh, the default would be na.rm equals true.
Yeah.
Yeah.
So you by default just remove them, right?
Yeah. Yeah. So it's not propagating. So if one value is nr, that doesn't mean like if everything is na. Yeah.
Yes, that's normal what you do, but
yeah.
Sometimes in R by default you keep the
yeah. Yeah, in R. Yeah. No, but I'm removing. Yeah. Exactly. So, and then I'm just building the data cube view with the spatial reference system, the spatial temporal extent. And now I'm just defining, I want to work at 200 meter spatial resolution and a daily temporal resolution. So this is for now, and this is how I now work, but there's no reason not to do it at higher resolution, except of course for the MODIS data then is like, downsampled. Oh no, upsampled quite a bit because the original resolution is so low. But anyway, so if you want to work on higher resolution, it's nothing else than just changing this number, actually. Okay, what I now do is I will separate data cubes, 3 different data cubes with the same geometry, and then I compute the NDVI value automatically. So this is a bit different because the band names are different. So for instance, for Sentinel, band 8 is the near infrared. For Landsat 8, it's the band 5. So again, it's kind of looking up metadata online and in the handbook. But yeah, as I said, so in principle, it would be possible if you adjust the collection formats to rename these bands to something like red or near infrared to get something more meaningful there. Okay, so I create these data cubes with a common data cube view, select the bands which are relevant, so for Landsat band 4 and 5, and then apply the NDVI formula, so the vegetation index, and the result is actually a data cube. And this is again a proxy object, so if I run this, it will not read any image data. So it will just know what it is, where the data is, how it looks like, and all that stuff. So it knows what to do if something needs to be done. So the same thing I'm running for the Sentinel-2 data. So I'm creating a separate data cube, compute the NDVI values based on band 8 and band 4, and store this as a Sentinel data as S2.cube. And then the same thing I'm doing for the MODIS data, and store this as a MODIS data cube. So that means I have 3 different data cubes now, or data cube proxy objects, but they come from different image collections, but they have the same data cube view. So the same data cube geometry. And that means actually that the size of the pixels, so the duration of pixels is exactly the same essentially. But of course, it makes a difference because the MODIS data has much lower spatial resolution. So what will be done is actually that it will be resampled and interpolated automatically on the fly. So you have to be aware of that, of course. So you can do many things, but of course you need to be aware of that it might not make sense if you do everything again on, I don't know, a 5-meter resolution. So you have to take care of it. Yeah.
Is this specific RCQ steps do you understand?
Oh, this is nothing, reading nothing. So this is just still images on disk, and it's just a proxy object. So it just knows where the data is and how it looks like and what to do. Yeah. So only if you call something like plot or write netcdf.
Only then you roll it down.
Yeah. Okay. But not the complete data actually. So you evaluate everything chunk-wise. Okay. So that you bits that you don't fill your main memory.
Sure, yeah.
Yeah.
Okay. It would be nice to see the computing progress.
There's a progress bar.
Yes.
Yeah.
It would be nice to see that. Did you do that in the first work?
I did that, yeah. So yeah, depending on the resolution and all that stuff, of course, it may take a while to compute things. So, but as I said, GDAL is actually pretty good in warping images and reading images. So I think that has a good performance, and yeah, there can be many things done actually. Okay, then the essential step now to bring everything together is the join bands function. And that takes a list of data cubes as input and optionally a list of names, so that we need later on. I'll tell you in a minute. And actually the requirement or the assumption here is that all the data cubes have the same geometry. So you have the same dimensionality and the same extent and resolution. So that is one assumption, but then it's pretty easy to bring them together. So the reason why in this case, it makes sense to add names to the data cubes is because all the bands of the input data cubes have the same name, and the band names must be unique. So I have 3 NDVI values from 3 different data cubes, and then I'm just adding the names as a prefix so that the result data cube, if I print it, you get something like this. And also, again, this is not reading anything, it's just a proxy object which knows the dimensionality. So you get actually, yeah, the dimensions, and then you get 3 different bands, which is L8.ndvi, S2.ndvi, and modus.ndvi. So we have unique names. So we have defined a prefix here for the NDVI names. And then it's actually pretty straightforward to analyze this data cube and combine the values from the different satellites somehow. So what I do in the first step now is I'm using the combined data cube. I call it combined.cube, and then apply the time reduction function and provide 3 different reducers. So apply actually 3 times count reducer, which counts non-NA values over time series. And once for the Landsat values, for the Sentinel values, and for the modus bands. And then I get actually a result with 3 different bands, but only 1 time slice that just shows you how many observations the data cube has from different satellites. So as expected, for modus data, you see that there you have up to 80 observations for some pixels. For Sentinel, it's in range of, well, maybe 30 to 40 or so observations, mostly. And for Landsat, it's actually only a pretty low number of observations, yes.
If you look at the plot name, there's a date up there.
Sorry, which plot?
That plot.
Yeah.
There's a date in the name. At the top.
Yeah.
Okay.
Because the reason is, you're asking because in the previous session we had a year, right? Or, oh yeah, so yeah.
The count refers to longer period, no?
Right. It reduced the time, but it still has a time information. So it's like, if you look here, it's a period of 215 days, 14 days. Yeah. And over that duration, we have aggregated. Yeah, right. Okay, so next step is actually to bring everything together to have only 1 NDVI value. And the most simple strategy to do it probably is like computing something like the best NDVI composite. So what I'm doing is here to define a color range so that we can plot the result quite nicely. But then I'm joining the data cubes again. And then I'm using the apply time function from the package. And this function is actually similar to the reduce time function with a user-defined R function we have seen. For instance, in the first part of the tutorial, we have created this greenest pixel composite image where we provided a R function to reduce time. This is actually pretty similar, except that the result is not reduced. So you get a full time series as input to the function you provide, but the result is still a time series. So you can change the values and compute new bands and everything, but the result is still a time series. And how you get it is as an argument, which is a two-dimensional array again. So where the first dimension refers to the bands and the second dimension refers to the time. So what we do here in this function is we first initialize our result with the data from MODIS. So we just copy the time series from the MODIS band and say, this is, for now, this is our result. So the next step is I'm going to check at which dates there are observations from Landsat. And if for these days where an observation from Landsat is available, I'm just overwriting values in my current result, which is the MODIS time series from Landsat. Because, well, for whatever reason, I think Landsat is maybe better because I work on 200-meter resolution and not on 500. And then I'm doing the same thing again. I say, like, well, maybe Sentinel-2 is even better than Landsat, and if Sentinel data is available, I'm again overwriting the result in my time series. And this is my final time series. So the result would be something like, so if you interpret something like Sentinel has better NDVI values, as Landsat, and Landsat is better than MODIS, which is questionable. But anyway, if you define it like this, this would be a strategy to create a best available NDVI time series, which is, well, maybe helpful if you want to really fill time series and get as many observations as possible for whatever method afterwards. So yeah, and then I'm plotting the results. So I'm only plotting a small part of the results at, I don't know, around 20 days. And yeah, you see that at some days there are actually available observations from Sentinel, obviously available, so you get higher resolution. But sometimes it's also a bit more blocky, where this is probably at these days where MODIS observations are available, but no others. So yeah, this is of course a very naive and optimistic approach, assuming that NDVI values of these sensors are comparable, which probably they are not because they have different spectral characteristics, and you probably would need to do a lot of more research to make sure that they are comparable. But as I said, so the purpose here is not to find the best method to fuse these data set, but to just show you how you can do it with the package, and then actually I hope you come up with better ideas. So I have one more example how to do it, but that's also very optimistic. So in the second example, the approach is that I use only Sentinel observations as actual NDVI values, but then derive something like the trend from the MODIS data. And that is also very optimistic, but I could be used to do something like completely fill the time series with NDVI values. So let's see how we can do this. This is actually pretty similar. We use, we combine the data cube with the join bands function. We apply a function over time series, an R function, and this function actually, as I said, it must reload all the packages again. So because this function is executed in a separate R process, so it cannot access any variables in your workspace. So you really have to reload packages again and all that stuff. So I'm using the zoo package to fill MODIS observations or fill the MODIS time series with a linear interpolation. So that is what the na.approx function does from the zoo package. So afterwards, I'm creating differences of successive observations and add one value to the beginning of the time series because, well, the difference is actually successive pairs of observations. And then, of course, there's one less pair at the beginning. So I'm just setting this to 0. And then I'm initializing something like my output result with NA values, but as many observations in time as the input dataCube actually provides. So what I then do is I find out at which time indexes we have Sentinel data. And for these indexes, I'm just using the Sentinel NDVI values. And for the others, I actually check what is the last available Sentinel-2 observation, and then I would successively add the differences from the MODIS thing. So the idea is actually you have the trend or the differences from the MODIS observation and then apply it to the Sentinel time series. So this is, of course, also very optimistic. And if you plot it, you find out that this is probably way too optimistic because NDVI values you get out of it are sometimes larger than 1 and or maybe smaller than -1. So you certainly need to do a bit of more thinking about how to make this better. But anyway, I hope actually this shows how you can do things with separate data sources and how to bring it together in one dataCube and then do things. And I hope that gives you some ideas what you could do with your own data. So are there questions on this example for now? All right, so let's go on with the second example. So yeah, our goal is actually in the second example that we want to jointly analyze satellite-derived vegetation data, but also precipitation data and soil moisture observations. And in the first example, we had something like modeling the same target variable. Now we have different variables in the dataCube. And we want to do something easy like computing correlations and anomalies and these kind of things. So also for this example, so the method I'm going to apply is very simple and straightforward. And yeah, it's probably not so meaningful. And what would you publish as something where you can infer really conclusions from? But it's, I think, a start how you can do things. And I think especially if you have like multivariable dataCubes with observations and variables from a lot of different sensors, especially this is very promising if you combine this with machine learning methods, where we could do something like learning how certain variables interact and all that stuff. So I think there's a lot of potential to do things there. But yeah, my expertise here is really on how you do things and not, also how you can apply things, but not on, yeah, show you the best method. Okay, so in this case, we're using also 3 different data sets. One is, again, MODIS, but this time MODIS 13A2, which is 1 kilometer spatial resolution, 16 days. It's kind of these best available pixel composite images. So you have images every 16 days, but actually you don't know exactly, or you can know, but so the pixels actually can result from different days because it's just selects the best available pixel within 16 days. But yeah, it's a pretty convenient data set to use. And then we use daily precipitation data set from the Global Precipitation Measurement Mission. In particular, it's this GPM3 IMERG DF and the GeoTIFF version, the GIS version from that data set, which lies on some FTP server, I think. And then we use some cool soil moisture data from the ESA Climate Change Initiative, which is really cool. So that's, I think, a 40 years soil moisture data set, which covers global areas and pretty useful. So probably very interesting to, to have and to look at more into detail. Okay, so the procedure is actually very similar to our first example. So what we do is just getting an initial overview of our data, creating image collections, and then creating dataCubes. So let's start with the MODIS data. So we list the files and store the path as a character vector, and print something where it is. It's again HDF files, HDF4 files. Then we create an image collection from it. So also for this Modus 13A2 product, we have an image collection format readily available. So that works out automatically, by the way. So yeah, then we have an image collection for the Modus data, and that references 1,404 images with seven bands. So it's a bit larger, this data set in this case. And yeah, again, it's this Modus sinusoidal projection. And well, bands are of course a bit different. So you have NDVI, you've already computed an NDVI value, but also some other vegetation indexes. And also you have a similar vegetation index quality band, which is also again these kind of bit fields, which requires you to read documentation very carefully. Okay, the same for the files from the Global Precipitation Measurement Mission. So these are GeoTIFF files, and also there's a collection format readily available in the package. Yeah, so we just list the files and create an image collection. And then in this case, it's also 1,462 images, also with 7 bands, where you have like separate liquid and ice daily accumulated precipitation, and total accumulated and total rate precipitation. That's pretty useful. And then we have also the soil moisture files, which are net CDF files. And yeah, we create an image collection similarly. We have also a collection format available, and then create a collection. And in this case, it's 2,556 images with 8 bands. That includes some uncertainty flags. Soil moisture, and also some uncertainty observation, which is pretty good to have. So yeah, these data are all, again, in very different formats. So for instance, and one thing you really realize when you work with Modus data or with these ESA soil moisture data is that the performance when you create data cubes actually depends highly on the input data format. So yeah, in this case, the soil moisture data set, for instance, is net CDF file, but that uses a deflate compression at level 9, which is the highest compression level. So when you read a subset of it, you need to uncompress the complete file, and it's pretty slow. So, and if you really repeatedly create data cubes from it and do it again and again and again, it might make sense to think about changing this data format. And therefore, the package actually comes with a function, translate GTIFF or translate COG, which is cloud optimized GeoTIFFs. And then certain things become faster. And that also generates overview images in GDAL. And that is one thing which is really cool to have, because that really allows you to work on smaller or lower spatial resolution really fast. So some data like Sentinel data, they kind of include already overview images, so like an image pyramid. But these Modus data, for instance, they come not. So that means if you read data at lower resolution, you really need to do the resampling on the fly and read all the data, all the pixels actually. So yeah, that's one thing, although GDAL is still doing quite a lot of things very good automatically. So, and GDAL also comes with all the utilities you need to create overview images, to convert imagery. So the package again is, in these cases, just like a batch function around GDAL translate actually to convert to GeoTIFF images. Yeah, so that might make sense. In this case, I still work with the original netcdf files just for illustration. But again, this example really, the code chunks take a bit longer than in the first session. So it's probably around 2 or 3 minutes each, which is still, well, doable, but also the data cube is actually pretty small in terms of spatial resolution. Okay, so let's then think about our data cube view. So how our target data cube should look like. So as an example, I just created something like an area around covering Germany. So at 5 kilometer spatial resolution and monthly temporal aggregation, temporal resolution. I'm using in the European map projection, which works out quite well. And so I'm doing not a median aggregation here, but a mean aggregation, because that actually for meteorological data in many cases makes more sense than for optical reflectance imagery. So then I'm just creating some color scales using the color space package for the NVI and for precipitation, and I'm using the precipitation scale also for soil moisture data. And then, first of all, I create separate data cubes with the same data cube view again. And then I plot this. So this is, for example, the NVI data, monthly aggregated from the MODIS data. And here you see that, well, of course, it's greening up in spring, and then at some point in autumn for 2018, it's getting yellowish again. So that's the NVI data. Then we have the total accumulated precipitation data, which looks like this. So here you also have data above the sea. And then we have the soil moisture data, which also contains a few NA values. So yeah, the soil moisture data, they're actually between 0 and 1, where 1 means fully saturated and 0 means completely dry. Good, and then we actually do some more pre-processing of the data. So the whole idea is actually that we may think, so something like anomalies in soil moisture or in precipitation or accumulated precipitation may have an effect on anomalies in the NDVI. So of course, in reality, these interactions are extremely complex and hard to model, and you would probably need a lot more data to do that properly. But still, we're computing and pre-processing these data quite a bit. So what we first do is for the NDVI data cube, we simply decompose the pixel time series into seasonal and trend components. Therefore, we use the STL function in R, which is quite convenient. And then we just use the remainder component and refer to this as the anomalies. So I know that this is not really like what you're doing with climate anomalies, where you have really like 30 or 40 years of data and then compute like monthly averages and then compute actually differences to that anomalies. So I only used 4 years of data and then did this season and trend decomposition. And yeah, this also can be done with the applied time function we had in the first example. And again, this takes a user-defined R function, which then gets individual pixel, multivariable pixel time series as input. Okay, then let's look at the code, what we do with the NDVI data cube. So we select the NDVI, so we omit all other bands and variables of the data set from the MODIS 13A2, and then we compute the, well, what I call NDVI anomaly. So I'm first using the package zoo again to linearly interpolate some values. There are not so many missing values, so this is really like only very few values that get filled. Then I'm checking whether the time series is like has NA values and still NA values, and if yes, then I'm just returning completely the NA time series, because then the decomposition may not work. Then I'm converting my time series to a TS object where I say that the frequency is 12, which means that we have 12 months, and then the cycle starts again actually. And I'm specifying that the start is 2015 first, or January. And then I can run the STL functions, which has some default values, but of course needs a lot of attention what you do there. So yeah, it decomposes the time series, and then we were interested only in the remainder and to return the remainder component. And that's what we call the NDVI anomaly cube. And also this is not really doing something yet. It's again a proxy object which knows what to do, but not, yeah, but doesn't read any data. So then for the precipitation data cube, we do, I think, a little bit of different pre-processing. So what we do there is we compute so-called standardized precipitation index, which is based on fitting a gamma distribution to all the precipitation values and then normalizing this to a standard normal distribution. So you get like really an indication if they have extreme values like -2 or -3, then this is an indication for a drought or yeah, something like that. And that standardizes, and it doesn't really, and it's applicable to different timescales actually, and yeah, works quite well for drought monitoring, I think. And luckily there's an R package for that. So I found this package, PrecentCon, I don't know how to pronounce actually, that can do that for us from monthly precipitation data. So, right, so we again get these multivariable time series as input to our out function, which we apply. And this object which comes in also has dimension names. So that means we can access the variables by name, and also the we can also access the time. So in this case, this is all represented as characters, but I can convert it to something like year and month with this expression. And then I'm building a data frame which has columns year, month, and precipitation, because that's what the R package, which I'm using to compute the standardized precipitation index, actually needs. And then there's one thing which is also needs. It needs a class, well, PrecentCon monthly. So which is nothing else than the data frame, but I just need to assign the class to get the other package I'm using to compute the index, yeah, to get it working. And then, yeah, I'm checking whether there are NA values in the time series, and yeah, if yes, I'm returning 1, and if not, I'm computing the SPI, standardized precipitation index, with the function from the package, and then I return it. So that means that I converted the monthly precipitation data cube, applying a user-defined R function to compute the standardized precipitation index. Good. For the soil moisture data cube, I'm doing something very similar to what I did with the NDVI data cube. So yeah, I'm compute something like trivial anomalies. So again, simply fitting, or decomposing the time series into season and trend components, and using the remainder component as kind of an anomaly. But before that, I still try to bring in the effect of several months into the time series. So, and therefore I compute a rolling mean before of 2 months of the soil moisture data. So yeah, but of course you can do anything there. This is just an example how you do things, but not like the most meaningful analysis. Okay, so now actually we have 3 data cubes, which with different kind of pre-processing, and the good thing is that they have used the same data cube view again. So similar to the first example, we can just bring it together with the join bands function. That's what we can do. So we provide a list with NDVI anomaly, precipitation, standardized precipitation index, and soil moisture anomaly. Yeah, and assign some cube names as prefix for the band names. And then, yeah, we need to think about some further analysis, and really, because I'm not like doing this very often, and I'm very interested in that, but I'm really haven't done much in that regard, is like modeling interactions between these different variables. So just as a first descriptive analysis, I'm just computing correlations with some temporal lag between these values.
Just a bit, what's the objective here? What do you want to compute? Because I'm reading also your tutorial, and I see you demonstrate algorithm analysis. But is just for the sake of demonstration, or you have specific hypothesis testing?
No. So the purpose is clearly just to show how you can do things, and this.
Well, keep on reading and looking into this.
Yeah. But you also missed the first part, right? So yeah.
Okay.
So yeah. No, it's just to illustrate that we can actually do complex things and processes within data cubes. And of course, there's no limit because you can use any functions that are available from other R packages.
And this one, Mauritia, for example, has lots of missing pixels.
Yeah.
And that doesn't make a problem for this analysis to find the decomposition.
Oh yeah, I'm filling just with linear interpolation, so that is very optimistic, yeah. Okay. And also the time series is much too short. So it's just like, I'm using just 4 years. So.
And the precipitation looks also very skewed. There's lots of, it's like a zero inflated.
Yeah, but that's the purpose of the precipitation index. So you fit a gamma distribution.
Okay.
So, and then normalize it to a standard normal distribution. Okay, anyway, so yeah, I can just go through this function, and then we're also approaching the end, actually, of the second part. So what we do is just compute then correlations with temporal lag between the different variables. So as a very simple, like, descriptive analysis, well, whether maybe there are interactions or there are correlations at least. And I'm using, the correlation test as well. So I test for correlation, which gets me a correlation estimate and also a p-value. Whether the correlation is equal to 0 or not. And yeah, so, right, let's see what the result looks like. And it's like this. So we have like correlations between the NDVI anomalies, the precipitation index with temporal lags 0, 1, and 2, and the same for the NDVI and the soil moisture anomalies. So yeah. Of course, I wouldn't use this analysis to infer some meaningful conclusions. But yeah, as I said, I think that may or may not stimulate some ideas because I guess there are someone from you might have more experiences in doing this kind of analysis. Yes. Okay, so that was part 2 of the tutorial, which was focusing on really bringing together data from different observation missions. Are there any questions so far? If not, then I have a third part.
I just have a question on the,
yeah.
There's this, I just sent you the link for Earth system data lab.
Yeah.
On your channel.
So this is a Earth system data cube. Yeah. Yeah.
So you think you could easily combine the gdalcubes in this?
Well, I know that they're implementing things in Julia, right? So probably there's some kind of a language barrier, but I think in principle, yes. But I think they pre-grid all the things and define. But I don't know actually. I have never looked into really the implementation details of the Earth system data cube, but yeah, I know that they have pretty many variables available in one data cube. Yeah, that's pretty cool.
Okay, thanks.
Yeah. Okay, so so my third part is actually just a summary and a discussion. And then at the end, you find some practical exercises, which you can work on if you want to do this. So yeah, what have we seen in this tutorial and also in the morning session? So I think this has demonstrated that how to create and process Earth observation data cubes, especially with the gdalcubes R package. And I hope that actually you see that there's a lot of potential for doing really cool analysis with data cubes. So yeah, the package makes actually some things easier. So it hides some complexities in the data, like different resolutions of spectral bands of different map projections of different images, some overlapping areas and data formats and all that stuff. And for that, actually, the whole library strongly builds on top of GDAL. So it uses GDAL for the more difficult things like reading data, writing data, and warping data in particular. So yeah, as I said, so the presented analysis have been rather simple, but I think the potential lies really on using all the available R packages and then applying them on dataCubes and to do really cool stuff. So yeah, I've also mentioned that the performance highly depends on the data formats, and something which is a good choice mostly is, well, having your data organized as a set of cloud optimized geotiffs, which are tiled and also contains overview images, so that you really can work interactively on lower resolution first, for example. Yeah, but of course, whether this is relevant for you depends a bit on what you're doing. So in many cases, if you're doing complex analysis, the computational bottleneck is actually running the algorithms, for instance, time series analysis or change detection, and rather than creating the cube. So that depends a bit on what you do. For simple methods, clearly it's the data cube construction that can be the computational bottleneck, but sometimes if you do complex analysis, it's not. So the data model in gdalcubes is limited to 4 dimensions only. So it has x, y, t, and band or variable. And one of the assumptions it does is it needs auto-rectified images by default. So it will not work directly for something like Sentinel 5P data or Sentinel-1 data. So you would need to add some additional pre-processing, like applying Sentinel toolbox stuff to the data, because they come with ground control points for Sentinel-1 data, or also they have these curvilinear grids, which are essentially latitude, longitude values for all the pixels. So yeah, one other thing I would like to mention is that it's not so straightforward as one might think to move analysis to gdalcubes to cloud computing environments. So the good thing is that, of course, in AWS and also in Google Cloud, that a lot of data are available, and the good thing is also that GDAL can read these data directly, but in many cases they are not in a cloud optimized format, so it's a bit stressful and a bit slow if you really want to only read parts of the images and then still need to download actually from the object storage complete images. So, and that's where I think the cloud optimized geotip format has pretty strong potential for future developments. And I think more and more data providers are essentially also organizing their collections as cloud optimized geotiffs, which is good. And then also sometimes if you really run your own machine on Amazon Web Services and you want to find the Sentinel-2 images, for instance, so there are higher level services, but sometimes also you end up with the CSV files containing like links to all the data, and so it's not so easy to discover. And so we need to do a little bit more work, and my hope is actually on the spatial temporal asset catalog, which makes this also a bit easier and is pretty much under development these days.
There's one question from the online.
Okay.
So the question is the NetCDF. You mentioned something that it can be inefficient, so very high compression. So if you keep the data in NetCDF, and if you have to keep on, pulling it to plot or something,
yeah,
it could be inefficient. So it's a good idea to translate it.
I wouldn't say that NetCDF is like slow, but it was only the particular case because it uses like the deflate compression with level 9, so which is really high compression ratio, which is really slow to uncompress. So, but otherwise NetCDF is fine. It's a good data format. Although I also see that there are quite a few developments to make this also cloud ready. So I think the Python world and from the OpenGeo thing, they have this ZAR data format, which is about to be integrated into NetCDF. I just read on Twitter yesterday. So that seems to be a lot faster than NetCDF for many cases, especially in cloud environments. So there seems to be many things going on.
In the GDAL, when it does like the GDAL work and resampling,
yeah,
it's not parallelized, right? You can parallelize compressions.
It can be parallelized. I don't know on compression. So the thing is, what I do with gdalcubes is I'm doing parallelization on a higher level. So I'm evaluating the data cubes chunk-wise, And then I'm checking how many chunks do I have in the output data cube, and then I compute them separately in different threads. So there is parallelization anyway. So you don't need to parallelize individual gdalcubes calls because there are so many gdalcubes calls, which gdalcubes actually does automatically, that you can parallelize anyway on a higher level. Okay, so other than that, my last point I want to make is, well, we have a lot of ideas for future work. So if you have any questions, any further ideas or find bugs or anything, so feel free to contact me or contribute in any other way. So feel invited to add something or also come up with interesting ideas, how to use the package for other things. Okay, thank you very much. So for the rest of the session, I actually suggest that you work on the practical exercise, and I will stop the presentation here. And I think most of you already downloaded this reduced size Landsat 8 dataset, which is like 2 gigabytes. And then you can really try out things with the package. So I have a couple of practical exercises here in the Markdown document of the tutorial 3. And yeah, you can try to solve these questions. There are solutions on GitHub as well, but please don't look them up unless you already tried to solve it. And then, of course, you could also try to reproduce the first part of the tutorial in the morning, which works in the same way as I presented with a larger data set. So I'll be around here and then try to help you setting up things and answering questions. Yes?
So I just have 2 questions.
Yeah, for sure.
It's okay.
Yeah.
So number 1 is I feel like scaling the analytical part, you know, you can really combine the time series analysis, but I feel like plotting, I think would make us work much faster with like plotting in QGIS and get, you know, somewhere else so it's not interrupted. Yeah. So just as soon as you have something that you don't go plotting R, but you call it in QGIS.
Yeah.
The RQGIS you know, you say this is the list of images, and they are the list, but then you have the list, right? Yeah. And so you would just call them in QGIS.
Yeah, I mean, what I do in plot is actually I create a file anyway, which is typically an .NETCDF file, but you can also create a collection of TIFF files from a data cube, and then it's pretty easy to visualize it in QGIS.
But if you have to, you know, turn on the legend always, you understand, like if you have a plot in R,
yeah.
you get the same legends and the organization of which is on the top, which is on the bottom, whatever layers.
Okay. So
then that would be something, you know, because I like R, of course, for plotting, but it's kind of compared. If you really want to see what you're working, then you can compare it with QGIS.
Yeah, sure. Yes.
So that's one thing, and then the other thing is, so do you have a process bar, everything you process? I think you show something. So that's, I didn't see that, but that's also usually what people ask for.
Yeah.
And then the last thing is this cloud OpenGeoHub. You make your own functions to, so how much is that different from the GDAL, just to do a GDAL translate?
It's calling GDAL translate, but
so
many times.
Just it, or is it anything special? Or? You just have our own just following that.
Yeah, it's just a wrapper for GDAL translate. And then, well, you can pass additional creation options to, well, change some settings.
Okay, that's it.
Yeah.
Thanks. Any other questions? Yes, okay.
I have a question about plotting. Is it possible to just for fancy plots to mask raster cube with a, let's say, polygon to get better shape than just square or something like it, or some animation purpose, for example?
There is actually a filter Geom operation where you can put a polygon in and then it, well, sets all the values in A, which are outside of the polygon. So that could be useful in that regard.